there's some reason that I don't have your test, then you better get it to me at some point real quick on Monday before I put it in as a 0.
Wait, what?
Maya,
The test.
I turned mine in.
I'll explain to you.
0.
I'll explain it to you later.
I don't really want to hear about it. That's funny.
I think you do want to hear about it.
No, she doesn't. Especially not until at least 2:30.
That's why I said later.
All right.
If you would
All
have
right.
eased in on the rest of our conversation.
Because, Joseph, we don't do all that crap in here, all that drama garbage, do
This
we?
isn't drama.
I love the drama. I literally love the
I
drama.
hate it.
Yeah, you also like find like a nice cold.
Oh, it
ice
makes my
tea.
day.
Oh my god, it makes me
I
want to
love
die.
Does biting people make your day?
Huh?
On this, we're going to cover a bunch today. You got to listen carefully and closely because it's a lot of information. None of it really difficult, but a lot of rules, a lot of different information that we're going to cover. So when Gwen goes off to her own little world back here like she does every now and then, she better come back quick. So it's got to be a quick flight, Gwen, all right?
Yeah, but why?
What's this symbol mean again?
Perpendicular.
Perpendicular. So perpendicular bisector. Perpendicular means they come together to form what? Right angles. Bisector means it does what?
What's into
Two equal parts.
2 equal parts. All right? So perpendicular bisector, we're going to talk about those. Angle bisectors. What's an angle bisector do?
Splits an angle into two equal parts.
Build right equations. We did this. What's that form called again? That was on the crossword.
Slope intercept.
Slope intercept. Good. Be able to use perpendicular bisectors of triangles. And this is probably these 4 here. They all sort of go together. And I have some triangles around that. I'll try to find them while you're copying down some of these notes. Define and use perpendicular bisectors of triangles, angle bisectors of triangles, medians of triangles, and altitudes of triangles. They all sort of go together, and that's why there's so much in this lesson, because they all sort of go together, and I hate to separate them, but it's just a lot of information all at once. Fill in what you need to fill in on this.
Yeah, this is what I meant to someone
Should have got these out a few days ago. I forgot about them. Now they're all good enough. Where Joseph, you can listen and do a couple things at once. See these? Lay them out flat. Grab some books off the shelf, lay them on it so they'll flatten out. Perpendicular bisectors, exactly what the name says it is. We talked about perpendicular bisectors a couple months ago. Very important. Perpendicular to and bisects a segment. So perpendicular to, so it's always going to be with a segment. So what it's going to do, you got some segment here. Then you got some perpendicular bisector that runs through that segment. That means it's going to form right angles with the segment, and it's going to split it into 2 equal segments. So if I'm looking at this down here, line DE, and it doesn't have to be a line, it could be another segment, could be a ray, could be whatever. But this time it's a line. Line DE, this line right here, is perpendicular to the segment, so it forms right angles, and not only is that a right angle, but all the rest of these are right angles also. And it bisects it. So this segment from here to there is always going to be the same as that segment from here to there. So segment AC has to be congruent to segment CB. Name me the 4 right angles in this picture. AC, D, give me another one.
B, C, D.
Say it again.
BCE.
BCE,
then AC.
All 4 of those are right angles. What's true about all 4 of those angles when you name them? That's
The
true.
C's are in the middle.
You got the vertex in the middle every time. So when you're naming an angle from that picture, if that C is not the middle letter in the angle, then you're naming it wrong. Thank you, Joseph. Fill in what you need to fill in on this. Just little boxes there. You probably have to write sort of small. You don't want to write small because you ain't going to be able to read it, then write it out to the side and take an arrow and point to it or something to fill it in. Whatever helps you out.
Would it be too dark if we turned the lights off?
Yeah, the front lights, I turned them on earlier because one of my classes was taking a test and I turned them back off.
Oh, that's better.
That's the way it normally is in here all the time. I just forgot today. All right, so what this theorem says, and there's actually 2 of them, but they're just sort of, one's the converse of the other. If I have a segment, wherever that segment's at, and I have the perpendicular bisector of that segment, we'll call this segment NT, and that perpendicular bisector runs down through it, splits it into 2 equal segments, and it forms right angles. I can pick any point on this perpendicular bisector. So let's say I pick this point right here. We'll call that H, that point there. That point, we'll call it S this time, is always the same distance from this end of the original segment as it is from that end. Now, if I had Sam come up and she put a point, where do you want to point at, Sam? On this segment, or on this line, or whatever.
Let's do under, like, H.
Tell me where to stop.
Like right here.
Right here. Guess what's true about Sam's point?
From C to T is the same as from C to N.
Those 2 distances are exactly the same. I have Maya pick a point. Where do you want your point at, Maya? Right here? There? So that's point M. Guess what's true about the distance from N and the distance from T? They're always exactly the same. No matter where you pick some point on the perpendicular bisector, it's got to be on that perpendicular bisector. Wherever you pick some point on that perpendicular bisector, it's the same distance from this endpoint of the original segment as it is from that endpoint. The converse of that, which we don't use near as much, but the converse says, if I draw something like this, if I have this triangle and I know that these 2 are the same, and I draw something that goes down through here and it splits this in half, and it splits that in half, it's also going to form a right angle. So this point is the same distance from this endpoint as it is from this endpoint, then that point is going to lie on the perpendicular bisector of this bottom segment here. This is the main one. Anytime you have any point that falls on that perpendicular bisector, it's the same distance from here as it is from there. Every time I do this, I do that point, we'll call that point J. What kind of triangle do I have right here? Every single time. It's always an isosceles triangle. Those two sides are always going to be congruent, and it's always an isosceles triangle. Guess what's true about this triangle and this triangle? They're the same. They're congruent. We just got done doing that whole chapter about congruent triangles. Those two triangles, every single time, are going to be the same. All kinds of information you can get just from that. Did I get rid of this on the paper? I think I did. No,
No, you got rid of.
Yeah, you-
I got rid of this. Because this is what's on there. Is GB the perpendicular bisector of that segment? Does it split the segment into two equal segments? Yeah, those two are congruent. Is it perpendicular to it? So then what do we know about point G? Same distance from O as it is from T. Those two distances have to be the same. So this says any point on, what are we putting points on?
GB,
Segment GB, it could be line GB, doesn't really matter, it could be array if you want to name it array. Is blank from point O to point T. Close. We're going to use this big word. Equidistance. If you wrote same distance there, maybe Joseph doesn't like equidistance, he just wants to put same distance, who cares? Same thing. So what do we know about point B?
It's the same from B to T and B to O.
So if I told you that this distance right here was 18 centimeters, what else do you know?
The other one.
This other one has to be 18 centimeters. Any point on that perpendicular bisector is the same distance from this endpoint as it is from that endpoint. It says find segment SR. First of all, is this a perpendicular bisector? It bisects it, and it's perpendicular to it. So what do we know about the distance from S to R and the distance S to P?
6.8.
So the answer there is 6.8. Can you tell me on this one?
The segment EF is 9.
Fill it in there. And we know that because we didn't know this time that this was a perpendicular bisector. Joseph, can you see? I'm trying to stay out of it. I'm trying to jump back this way every time. We didn't know that that was a perpendicular bisector, but we knew that it was the same distance from, H was the same distance from E as it is from G. That tells us it's a perpendicular bisector, so that means these two segments have to be the same. What can we do on this one?
3x plus 14 equals 5x.
This is a perpendicular bisector. That means this distance has to be the same as that distance, so 3x plus 14 has to equal 5x. How are you going to solve that?
Minus 3x.
Gives you 2x over there, equals what on this side?
14 to 7.
Is that our answer?
No.
No, they said find what?
CD.
Now, when you go to find CD, because we don't want to make anything any harder on Allie than it has to be, do I want to plug in here?
No.
Where would be an easier place to plug in?
5x.
Plug in here, make it easy on yourself, because what do you know about these two segments? They're congruent, they're the same. How much is this one?
35.
So how long is CD?
35.
35. Pick out whichever one's the easiest. Don't make anything harder on you than it has to be. Fill in what you need to fill on this angle bisector. We've never ever talked about angle bisectors before, this is the first time, right?
No, yeah, sure. Now it is. You forgot everything you was doing by yourself?
There's more you gotta fill in. Still more. Still more now. So an angle bisector, ray that splits an angle into two congruent angles. Tell me the angle bisector in this case.
TH.
TH, make sure you fill that in. So ray TH. What angle's being bisected?
NTS.
The blue angle here, NTS. Tell me the two congruent angles.
NTH.
Does everybody agree with her on that?
Yeah, and then
ST.
Those two angles have to be congruent every time. Angle bisector, we've talked about that several times throughout the year. I'm just reintroducing it because it's going to be useful here in a few minutes. Fill in what you need to fill in on this. Whenever we're finding the distance, if I'm going to find the distance from me to Juliet, how am I going to walk to her?
straight line.
All lines are straight. Do I want to walk like this?
No.
I mean, you could.
Is that how I'm going to get there? You want the shortest path. That shortest path always has to form a what with her? When we were doing shortest path at the start of the year,
Right angle. No.
if you're standing here and you're trying to get to this line,
You could put a right angle,
you got to come down here and it's got to form a
Right angle.
right angle every time. It's got to be perpendicular. Anytime we're talking about distance, you got to see that right angle there. So if I'm standing here and I want to walk to Julia, I got to make sure I'm forming a right angle with her line there. Get it all? Again, if you can't fit it in the boxes, I'm going to have to figure out something with this. I don't know. Can you read it? So if I draw an angle here, and I'm going to bisect this angle, so I know that these two angles are congruent. What this theorem says, just sort of like the perpendicular bisector theorem, I can pick any point on this angle bisector, wherever it's at, and it's always going to be the same distance from that side of the angle to that side of the angle. Those two distances always have to be the same. Now, to be a distance, those have to come out here and they have to form right angles. You can't just put a point here and say, okay, that distance is the same as that distance. That's not going to work out. The distance has to be the shortest path. It has to form a right angle with the side. The converse of that says, if these two distances are the same, then guess what's happening to this angle back here? It's being bisected. So you might want to mark those in. Those angles there have to be congruent to each other. So any point on this angle bisector is the same distance from this ray as it is from that ray. So if I pick some point right here, and it comes out there, that's a right angle. Comes out here, that's a right angle. What do I know about those two segments right there? They're the same, they're congruent. What do I know about these two segments over here? Segment BD and segment DC. They're congruent, they're the same. Any point that you pick anywhere on that is the same distance from one side of the angle as it is from the other side. That's the angle bisector theorem. Is this angle being bisected? So what do you know about these two segments? So tell me an equation when you set up.
6x.
Does it matter which order?
No, 5x plus 6x. You're gonna equal 6x plus 5.
I probably would have did the 6x first, but that's all right. Because here, if we do this, and this is what a lot of you would do. That's probably why I put this problem on here this way. What happens with the 5x's?
It crosses out.
Cancel out. What do you have over here?
1x minus 5.
Guess what happens with that?
Wait, wait, wait.
People get confused because there's no equation anymore.
B equals 0.
You have to have that equal 0. Now what are we going to do to solve?
Add 5.
Add 5. Ignore the stray marks going up through there. So now what's x equal? 5. They said find the length of segment PS. How are we going to find that?
5 times
Plug
5.
it in.
Plug it in right there. 5 times 5. What is 5 times 5?
25x.
How long is segment SR?
25.
25. How long is segment PQ? Good answer. No idea. Staying on fat, aren't you? Why are you so mean? On this one, what do we know about these two segments? They're the same. If they're the same, they both form right angles here. Guess what's happening to this angle? So if this angle's 42, what's this angle? Now be careful. What angle did they ask us to find?
GFH.
So it's 42.
No.
Angle GFH is how much? How are we going to find it?
44.
42 plus 42, which is
84.
84 degrees. Make sure you read the problem carefully. Number 1, anybody figure out what x is on number 1?
5.
Not too difficult. Number 2, anybody tell me an equation?
X plus 7 is 15.
Does everybody agree with Sam on that? What's x equal then?
8.
Number 3, how about that one?
2x plus 1 equals 5.
What's x equal? I'll let you guys solve it.
2.
2? How about 4?
2x plus 9 equals 3 minus 4x.
Ignore that stray mark going up through there.
X equals 3.
X equals what?
3.
Are you?
That sounds right.
No.
Yeah, so
It equals 2.
I got
Negative 1?
I got
Oh,
3.
minus-
I got 3x.
Well, if you
X
add
equals
4
Tell
3
me.
and I got it.
Tell me how to do it.
Add
So-
4.
Hold on, let me rewrite it. Let me rewrite it because I'm not going to be able to do it there and
Yeah, I got 3.
show it very well. So 3 minus 4x.
So I took minus 2x from both sides.
Now you got to be careful here if you're going to do that. These cancel. What's left on this side?
9 equals 3 minus 2x.
Careful. You owe me 4 x's and you borrowed 2 more x's. Where are you at?
Negative 6.
Negative 6x. Now what?
Add minus 3.
Subtract 3 on both sides. What's 9 minus 3?
6.
I'm going to write it down here. What's still left on the other side?
Negative 6.
Negative 6. Now what?
Divide.
5.
Negative 6.
These cancel out and leave you with just x. What's 6 divided by negative 6?
Negative 1.
Negative 1. Good. Is it alright for x to be negative 1?
Yeah.
Doesn't that mean our side's going to be a negative?
No.
Not necessarily. We can plug it back in here and find out, right? What's 2 times negative 1? Negative 2 plus 9.
7.
So that side's alright. Let's do this. What's a negative 4 times a negative 1? Positive 4, what's 3 plus 4?
7.
So it worked out to where the segments are all positive, right? And that's what matters. Segments and angles have to be positive. Writing equations of perpendicular bisectors. Nothing for you to fill in on this. I just want you to listen because we're not going to do a whole lot with this. We did this earlier this year. Some of this, you just got to know how to do it. And these are the steps. Graph the original segment. So if we just make up some segment here. Let's go there. And we'll put a point here. So that's our original segment. We'll call it NT. Find the midpoint of that segment. What are we going to use to find the midpoint of a segment?
Take that equation.
That midpoint.
Midpoint
Equation.
formula, right?
Yeah.
So we do that, we find the midpoint. If I'm looking at this one, and I'm not going to use the midpoint formula, it's going to be somewhere about there, right? Don't do that. Don't just estimate, but that's where the midpoint's somewhere close. If we found it, it'd probably fall about there, right, Ginger? Find the slope of the original segment. How can I find the slope of segment NT here? 1, 2, 3, 4. So up 4 over 1, 2, 3.
Negative.
And it's a negative. So negative 4/3 there. That's the slope of the original segment. What should be true about the slope of something that's perpendicular to it? So that other, whatever it is that runs through here and is perpendicular to it.
Opposite reciprocal.
Opposite reciprocals. What's the opposite reciprocal of 4 over negative 3? 3 over 4. We did that stuff earlier this year. Use the midpoint and the slope to find B. So you're going to take the midpoint, whatever the coordinates of that midpoint are, stick them in here and here for the midpoint, and the slope and stick in there and find B. We did that earlier this year. Once we know what B is, and once we know what the slope is, we're going to write our equation in slope-intercept form. So y equals, we'll put in a number. Our number this time is 3/4 for that. So y equals 3/4 x. We didn't actually figure out what b was, but we could have figured out what it was, and we'd stick that in there. That's our equation. Again, we wrote those equations earlier this year when we were doing some of this stuff. Don't forget about that. Sorry that your picture is ugly on this one. Fill in what you need to fill in there. I couldn't figure out how to fix it, and I got tired of trying. Got to know this word. Concurrent and concurrency. The point of concurrency is where a whole bunch of lines come together. That point right there is the point of concurrency, because all 3 of these lines cross there at that point. Very important, all right, for what we're getting ready to do. So that's called the point of concurrency. Where they all cross at, where they all come together. Nothing really hard about point of concurrency or concurrent, except for it's one of those words that everybody likes to forget. Like on the vote or on the crossword, stuff like conjecture and perpendicular, you guys seem to have trouble with, and everybody, I'm not sure why. Fill in what you need to fill in on this. Again, this is another one of those things that we're not going to do a whole lot with, but as the year goes along, you're going to need to know these definitions. Something's inscribed. What's that tell you? If I say this is inscribed, should be the first word that pops into your mind.
Inside.
Inside. My wedding ring here, my wife inscribed in it how much she loves me and everything.
Is there nothing?
Yeah. My wedding ring got stolen several years ago, so.
No way.
So this is a
That's so cool.
replacement.
Really, not the fact your wedding ring got stolen, but like,
Where did it get stolen from?
like, how did your wedding ring get stolen?
Yeah.
If it's on
Can
your
we hear the
finger.
It wasn't on
story?
my finger.
Where was it
It
then?
was in the jewelry box
Why weren't you wearing it?
because I was working on my car.
So someone broke into your house and stole your wedding ring?
Yeah, when I went there, because I didn't put it back on my finger after I go out and work on the car. My old wedding ring, it catches. When you got it on your hand and you're working on something and you're reaching in there, it catches a lot. So I took it off, put it in the jewelry box whereas I was working on my car. And then somebody broke into our house and stole the jewelry.
See, it's not cool that it got stolen, but it's cool like how that works.
So anything that's inside here, something that's inscribed on the inside of this. Now that's a little different than this. To be inscribed inside a circle, all the corners of the shape have to touch the circle. So if I had a shape of some quadrilateral, and I did this, is that quadrilateral inscribed in that circle?
No, because one point's not touching.
It's not inscribed. All the corners have to touch it. So I could take some pentagon. And if I could draw better. And they all touch. Let's fill this in here somewhere. A circle. What do you know about a circle? How many degrees? 360 degrees. You might want to write that down somewhere. That's something you don't need to know. So, if I'm inscribing something in a circle, let's say if this triangle here, it doesn't look like it right now, it looks like it's a nice, well, let's just go with it. What kind of triangle does this appear to be? So these two sides are congruent, right? Guess what has to be true about this part of the circle and this part of the circle? They have to be the same. So if I told you this part of the circle down here was 50 degrees. Yeah, let's make it something easier, man. Let's go 60 degrees. How much is left over for these two parts? 300. How much is this part from here to here? Close. 150. How much is this part over here? 150. A circumscribed. As soon as you hear, if inscribed means inside, circumscribed, what should you think of? Instead of inside, it's outside. And that's what this is. Somebody describe this shape, this picture right here to me, using inscribed.
The circle is touching 3 of the sides of
The circle is
inside.
inscribed in the triangle. Describe this picture using circumscribed.
The circle is circumcised.
I knew that was
Scribe.
gonna happen.
Circumscribed
I didn't realize this.
about the triangle.
Sorry. You're not even mad because you know it's kind of funny.
I did that in 7th grade.
I'm not mad because
We're doing
I've been doing this for too long.
circumcision.
Fill in what you need to fill in on this. Now we're to the hard stuff.
Is that name for these parents?
Circumcision.
Is that how you say it?
It's not just a mess.
Circumcenter? Okay.
Some bored.
I know, but I just make sure that's how you say it.
I was guessing. That's why I said it out loud. See if you correct me or not.
Yeah, I'm too scared to say it out loud. No. Like Julia.
Now, there's going to be 3 theorems that we're going to talk about today, and all 3 of them are sort of important. You got to be able to deal with them and use them. and know them. Perpendicular bisector of a triangle. Perpendicular bisector of a triangle is perpendicular to and bisects one of the sides of the triangle. How many sides does a triangle have? So if a triangle has 3 sides, how many perpendicular bisectors is it going to have? 3. So you might write down there are 3 perpendicular bisectors for a triangle. Every triangle's got 3 perpendicular bisectors. And every triangle is going to have 3 of all these things that we talked about over the next few minutes. So if I drew this, and this in no way, shape, or form is correct, but if I drew all the perpendicular bisectors of this triangle, they all come together at a point. That's called the point of concurrency. And 4 perpendicular bisectors, that point of concurrency, where they all come together, is called the circumcenter. Right? That circumcenter, that exact point, going down to this theorem, is the same distance from this corner as it is from this corner as it is from this corner. So wherever that circumcenter is located, whatever the triangle is I have, wherever that circumcenter is located, it's the same distance from here as it is to there, as it is to there. Every single time. Every triangle in the world, that's the way it works. All right? And we're going to draw pictures of it. That's what those 3 triangles are for there. So things to remember here. Perpendicular bisector goes with circumcenter. Got to be able to put those 2 things together. The bad thing is that's not the only one. There's going to be 3 others that you got to put the 2 things together like that. If I'm going to draw, and I know some of you, if you got a ruler or something there with you, you can, if you're real particular about how your picture's drawn, then you might want to get that ruler out so you can draw straight segments and everything. I'm not going to draw mine all perfect. If I'm going to draw the perpendicular bisectors for this segment, if I pick this side right here first thing I want to do is I want to bisect that side. All right? Somebody tell me about when I get to the midpoint. I'm going to move my pen up this. Tell me when I'm at the midpoint. Now, this is what I want to do. To make this easier on me, let's do the same thing on this other side over here. Tell me when to stop. Do the same thing on the bottom. Let's find the midpoint. So that's where we're bisecting the segment. Now we want a line that runs through that and it forms a right angle. We want it to be perpendicular to it. Am I going to draw something that looks like this? No, it's going to come and it's actually going to look, if I can draw straight, something like that.
So it goes with an angle?
This time it does. It doesn't have to.
Okay.
For this certain triangle, because what kind of triangle do I have here? It appears to be what kind of triangle? Equilateral. On an equilateral triangle, it will run right to the angle. Same idea here. That's a right angle, that's a right angle. And then same idea here. That's a right angle. Notice, if I could draw straight, they all 3 intersect at one certain point. That point is the circumcenter. Now what that theorem says, I'm going to change my ink color here. What that theorem says, I didn't really need to change it this time, but this circumcenter is the same distance from this corner as it is from this corner as it is from this corner. So as I'm looking at this distance, that length of that segment has to be the exact same as the length of this segment and the length of that segment. All 3 of those have to be the same. And if you drew it straight and everything, but better than mine, you could probably tell that all 3 of those distances do look the same. the next one, what kind of triangles this look like it is?
Isosceles?
Right triangle.
Looks like at least a right triangle, right? Might be isosceles, like, yeah, I'm not sure. So it looks like there's a right angle there. Doesn't have to be a right triangle. Tell me when to stop when we find the midpoint on this side.
Stop.
Tell me on this side.
Stop.
This side. Now we want to be perpendicular to this. I'm going to use my yardstick here. Is it going to go down there and do that?
No.
It's not going to hit that corner this time, is it? So tell me when I'm at a right angle with this side of the triangle as I'm moving this around. Not yet?
Stop.
About there? Does everybody agree with that? So something coming straight across like that?
Yeah.
Notice, this perpendicular bisector just runs, it just runs out wherever. It doesn't have to hit a corner like it did over here. Tell me when I'm at a right angle with this bottom side. Really?
Up there.
There?
You said really?
So something like that, that's a right angle. Now I'm going to do the same thing for this side. Tell me when I'm at a right angle with this side. If I can do it, I can't get my ruler far enough. There?
You guys did angle it.
Something about like that? That look pretty close.
Yeah.
They all come together. If I drew this right, if you were drawing it on your paper, guess where they actually fall?
On what?
They fall right there on that side.
That's what.
They actually fall right on that side, if it's a right triangle. What's that point called again? The circumcenter. That circumcenter is the same distance, if I've drawn it correctly, it'd be right here. It's the same distance from this corner as it is from that corner as it is to this corner. So those three distances, that distance, and this distance, all three have to be the same. If it's a right triangle, it's actually going to be the midpoint. The circumcenter is going to be the midpoint of, what's this side called in a right triangle? A hypotenuse. Tell me when I'm at a midpoint for this side.
There.
There? Is that about right?
Yeah.
How about this side? There? Is that all right? This side?
There.
Start over, I went too quick. There? We want to form a right angle with this. I'm not going to get my ruler back out. It's too much pain, but it's just got to form, it's got to go. Does that look about like a right angle?
Yeah.
You might have to turn your head a little sideways.
Look first.
This one, I'm going to take that on up. This one's going to come like right down through this, right?
Yeah.
Something about like that. This one, maybe I better get my ruler back up. Does that look like about a right angle? Right here?
Yeah.
Pretty close. What do you notice about the circumcenter this time?
It's outside of the triangle.
That's your circumcenter. What kind of triangle was this?
Isosceles.
Maybe. Give me another name.
Obtuse.
It's an obtuse triangle. On an obtuse triangle, the circumcenter falls outside the triangle. Now, look at this. The distance from here to here, does it look about the same as the distance to here? Those two look about the same? And does that look about the same as this distance? I know you can't hardly see it. I should have changed my color, shouldn't I?
I mean, I feel like one of them looks short, but this one.
That's probably my terrible drawing. So this distance, and that distance. Those three look about the same. If I could draw a little better,
Yeah,
almost looks like a pyramid or something, doesn't it?
that's what, yeah. That's what-
Three-dimensional.
Yeah.
Didn't know I was that great an artist, did you? I tell Mr. Holster, I'm a better artist than him. Fill in what you need to fill in on this as soon as I get out of the way. No. This is the one that I actually drew, and I took my time and drew it. It's a right triangle. Guess where the circumcenter fell at? Right on the hypotenuse. And the distance from that point to each of my two hands, exactly the same. The distance from here to this corner, exactly the same as the other two distances. Median. As soon as you hear median, what should you think of?
Middle.
I don't like the word middle, so
Midpoint.
midpoint. Median and midpoint go together. Median of a triangle is a segment that runs from a vertex. So it does have to start at a corner. Perpendicular bisector didn't have to. All of the rest of these have to start at a corner. So it starts at a corner of a triangle, and it goes to the midpoint of the opposite side. So if I draw this triangle, got triangle ABC. Pick me a corner. B. Which side is opposite angle B? What is it? Segment what?
C.
Just C?
CA.
That side is the opposite side. So a median does this. It starts here, and it goes to the midpoint of that opposite side. That's all a median is. Starts at a corner, hits the midpoint on the opposite side as it's going through it. That's a median. If you draw all three medians of a triangle, again, it's all every triangle is going to have three medians. If you draw all three, the point of concurrency, the point where they all come together, is called the centroid. Centroid. I can tell Gentry's head, he's thinking about some silly video game or something that, don't lie to me, Gentry, I know what was going through your head. Centroid, I've heard that before on Space Wars or whatever, some video game, I
What's
don't know.
that?
I don't have any idea.
What
I don't know any
else?
video games. So centroid is the point of concurrency where they all come together. The centroid theorem, this one's sort of hard, so listen closely. The way I explain it, the second way is not hard. It's sort of easy, but it's confusing. The first way, you got to know both ways though. The centroid is 2/3 of the distance from the vertex to the midpoint of the opposite side. So if I tell you that the centroid is right there, that point is your centroid. The way this theorem is saying, it's saying that this distance is 2/3 of the entire distance. So if this part is 2/3, that means this part over here is what part? 1/3. Now a lot of students don't like that because you're stuck in fractions there. But if I told you that this whole distance was, let's say 30. If that whole distance is 30 from B to the midpoint here, how long is this segment from B to M going to be? 20. How long is this part down here going to be? It's that simple. Don't make it harder than it is. 2/3 and 1/3. All right? Another way to think about it, the distance from the centroid to the vertex is always twice the distance from the centroid to the midpoint. How long did you tell me the distance from the centroid to the vertex was? To the corner? 20. How long was it from the centroid to the midpoint?
10.
What do you notice about 20 and 10?
They're factors.
20 is twice as big as 10. That's the other way to think about it. So on these, we're going to draw this, all the medians. Can you do it without me running my pen through here and finding the midpoint again every time? Can you guys just sort of estimate on yours? Maybe it's about there, about there, about there. The good thing this time is when you draw these in, it always starts at the angle, starts at the corner. You'll notice that on mine I have to draw my points really big sometimes to cover up my mess up where they don't actually hit each other like they should.
Does it matter where you put the angles? Like where you start for the points? Like can it go any direction?
What do you mean?
Like say for the bottom isosceles on the left, does it matter which one you start at?
Oh, which angle you start at? No. Did your picture come out looking like that?
Yeah, I was just wondering.
No, the centroid's going to be, they're all going to connect there. If I could actually draw well, they're always going to hit at that certain point all the time. So now I'm looking at this centroid right here. What do I know about that distance in relationship to this distance?
It's 2/3.
This is 2/3 of the whole thing. If I told you this this part from here to there was 50, how far would this one be?
75. I mean 25.
25, it'd be half of it, right? What if I told you this distance was 7? How far would this distance be?
14.
What if I told you the distance from this point to this corner was 9? What would this little distance right here be? 3. And what would this distance from here to there be?
6.
6.
That's what you're doing every time, just figuring out now. What I just drew up here with all these numbers, not physically possible. You're not gonna have one of them 50 and another one 3 in that same triangle. Alright, but, so that's the centroid. Centroid. Point of concurrency for median. As soon as you hear median, midpoint, and centroid. Think of those two words every time. You put them all together. Fill in what you need to fill in on this. Gwen, you sort of getting the idea on all this?
Yep.
It's just a lot of information, not really difficult, is it?
Nope.
Just got to make sure that Ebersole gives you a whole bunch of vocab tests here in the next week or so to make sure you got them all memorized.
I think we're
No.
good. I think we're good, actually.
We'll see.
How about you only speak for yourself?
Hmm?
So you want a vocab quiz? Though?
No, I don't.
Okay, so I'm saying we don't need one, too.
You said we're good, made it sound like you were okay, like you think we're gonna do good for it.
No, we're good. We don't need one. We're good.
I love teenagers. They don't know what each other's talking about. They don't listen to each
Oh,
other.
we were there mentioning Abby, Kaylee, and Ginger all arguing, and we're all laughing.
Yeah. About what?
Because they're all arguing about the test, and
oh,
they're literally
yeah.
yelling, like they're yelling at each other.
And the bad thing is they were probably all correct about whatever they were yelling about.
Yeah.
Yeah.
They just weren't listening to each
There's
other.
Yeah,
two
they
different
were-
conversations.
I didn't see it.
Angle bisector of a triangle again. Every triangle. How many angles does a triangle have?
3.
So it's going to have 3 angle bisectors. All right. Every triangle is going to have 3 angle bisectors. The point of concurrency of the angle bisectors is called the end center. The way I remember end center for angle bisectors, if I'm bisecting the angles, I'm just splitting all these angles up evenly. That point's always going to be where in this triangle? Sort of in the center. Now, it's not exactly in the center, but it's inside the triangle every time. The end center theorem. This may be the most important theorem of all 3 of these. The end center theorem is equidistance from the 3 sides of the triangle. The end center is. So this point, if you find that end center, if you find the end center, it's the same distance from this side of the triangle as it is to that side of the triangle, as it is to that side of the triangle. Remember, distance, mine doesn't look like it because I make my points too big. Distance always has to be the perpendicular going out to those. But those 3 distances always have to be the same. That other theorem we said that it had to be the same distance from the corners of the triangle. This one says it's the same distance from the sides of the triangle. So they're sort of similar to each other, but just dealing with sides this time instead of the corners. When you draw these, what are you going to try to do for each one? If it's an angle bisector, what are you trying to do to each angle?
Bisect.
You're trying to bisect it. So all you're doing is splitting it in half. So go through, and you're going to try to get exactly halfway in the angle. So it's always going to start at an angle, and it's going to go to the other side somewhere. So just try to bisect each angle. Try to split each angle up in half. Again, mine's not drawn very well. Hopefully yours is better. Just splitting each angle up in half. If it helps you, like it would help me with my drawing, mark the angles. We know those 2 angles are congruent. We know these 2 angles are congruent. We know these 2 angles are congruent. got lazy there. Used in center on 2 of them instead of 1. Again, mine didn't look like it, but these 2 angles should be congruent. These 2 angles should be congruent. These 2 angles should be congruent, so on, so on, so on. The distance, again, the distance from this end center to that side of the triangle, it's going to form a right angle. To this side of the triangle, it's going to form a right angle there. And to this side of the triangle, it's going to form a right angle there. Those 3 distances always have to be exactly the same. Last one. Altitude of a triangle. What's altitude mean? How high? How tall? Altitude of the triangle. When you're thinking of altitude, that's the height of the triangle. But the bad thing with height is every time I say height to a teenager, they think what? Which direction are you going? Up. That's not the case. If I'm looking at this triangle right here, is the height this? No. Right? Depends on how the triangle is oriented to you. All right? So height can be different. An altitude of a triangle, again, every triangle is going to have 3 of them. Every triangle has 3 altitudes. Altitude runs from one of the corners to the opposite side, and it forms right angles. So every time you hear altitude, you should think of right angles. Every time you hear the word altitude, think of right angles. What do you notice down here that's missing?
Are we not doing?
It doesn't have a what? What was on all the rest of them? There's no theorem for this one. Right? There's no theorem for this. You just got to know if it says altitude, it's going down there, it's forming right angles. The point where they all meet is called the orthocenter. Orthocenter. See if you can do this. All I'm going to do on this one, I'm going to show you how to do this. For this one, every one of these is going to be a little different, so this is a little harder. We go from this point to the opposite side, and we want it to form a what? A right angle. How am I going to do that with this? Let's get my ruler out again. Tell me when I'm right at a right angle with that opposite side. Right there? That's a right angle?
Yeah, it's gonna be slanted into a triangle.
That's a right angle? Keep going. Is that a right angle?
You're not gonna get one, right?
I'm not going to get one?
Inside of the triangle.
There you go.
Ah, so what are you going to have to do? It's going to hit this side of the triangle, but what do we got to do to that side of the triangle?
Add on.
You got to extend it on out. So it's going to look something like that. Same idea with this other one. If I'm going to form a right angle here, coming and hitting this side, this side's going to have to be extended on out. I can't do it on my board because I'm way down here somewhere. So it's going to come down here like this. Where's the orthocenter going to end up falling for this triangle? See that flower right there? The orthocenter is going to be somewhere about there. Let's do the orthocenter on this one. We want it to go from here and form a right angle. This one's not too hard. Any equilateral triangle is not too difficult. Right angle. Right angle. On the equilateral triangles, what do you notice about all the points of concurrency?
Same place.
They're all in the exact same place because it's an equilateral triangle. So orthocenter, circumcenter, end center, centroid all the same. A little tougher on this one. Does that look like about a right angle?
Yeah.
That's pretty easy. Where's the right angle going to fall? Tell me when I'm at a right angle with this opposite side. Not yet?
What about there?
There?
Keep moving a little bit.
So what happened here? If it was a right triangle, it's actually,
Already.
the altitude is one of the sides of the triangle. Guess what happens with the other one?
It goes straight up.
It's the other side. If it's a right triangle, these two sides, the two legs, are altitudes. Where do they all intersect at? Right there at the corner of the right angle. That's the orthocenter. Yeah, orthocenter. Confused myself. Is it always going to be that way?
No.
No, we could have some other triangle and maybe it's, of course I draw a right triangle. I don't know if I can draw anything other than that. Not really. So this one's going to come straight down here. This one might come over here, something like that. This one's going to come over here, something like that, and form a right angle. That orthocenter is going to be somewhere like in there. Different for every triangle. If you didn't grab the packet up there, grab it real quick. Grab a paper towel while you're up there so we can wipe off the desk.
I got you guys. Stay back there. I got you.
You got me, Sam?
Yeah.
Sam, you got me?
I was trying to be nice, but then Gwen was like, shh. I'm gonna smack you. It's like this.
Do it at 2:30. Me and Joseph don't like the drama.
I love the drama.
So I can smack her at 2:30?
No, he was talking about me smacking.
As long,
What did you just do? Julia.
as long as you're away from room 206 so I don't have to see it.
So if I'm in the stairwell, that's not
I'm
so
gonna do it so, like, right in the doorway, so you have to be able to.
No.
That's what that noise was?
We got time today.
You're okay. Then what about that vocab quiz?
We might have it if you do it.
If I do it, we'll
We'll
have
have
it.
a long
If
one.
I don't do it, what we have to do?
The server smells like
You don't
I
have to
got
go.
it at 2:30.
Not next
Oh,
class.
Ebersole did it too.
I literally got her at Ebersole just looking at me like I'm stupid. Thanks, Alex.
You have them. Are you trustworthy?
I got you one.
No, you didn't get kicked out.
Oh, paper
No, you're
towel.
not trustworthy.
Did I give you a packet?
Oh, I can be normal.
Write your name on there. Put the pages you have. And stick it in the tray for me. I'll trust you this time. Joseph, don't say stuff like that, man. Allie's trustworthy. I don't know why you're being mean to her, saying she's not.
What did he say?
He said Allie wasn't trustworthy.
My head just triggers. I have these things in my baby.
Why am I not trustworthy?
Because you bite people
Because
and
you
then
bite
you tell
people.
on them.
No, you bite yourself and then you say other people bit you.
That was so good.
Maybe that's fair enough.
Oh, shit.
That's good power. That's what.
It's Jeepers Creepers.
No, it's shiver me timber.
Get those for somebody else? Who are you gonna
Jeepers
for?
Creepers.
Clinton's one of the few that's been pretty about doing his work when he's not here.
It's because Maya's here.
It's for my
The bad thing is that he's not here too often.
He's quarantined.
Right, that's why he shouldn't have missed all those other days where he just felt like staying in bed and not getting up.
Exactly. Yo,
Can you spray mine?
where'd you go? Did you?
I feel like staying.
Why
every
else?
day.
What if you just saw it last
My
time?
mom comes in my room with
I'm
a
not really lying.
Who is it?
sprays me until I
Did he
get
look
ready.
at the quarantine?
I hope she's safe.
Oh, yeah.
Let's tell her safe. Safe. Let's tell her safe.
It was just mix up right now. It was with her.
I'll tell her.
Do me a favor, put up some of the chairs around you.